Alright, this is the last day of new stuff for the unit. Monday we'll review, Tuesday we'll test. Note to self, I need to put that test in for copies. The stuff we do today, it's always tested on the AP test, but it is almost always, you can never say always, I guess. I don't think it's ever been on the free response part. It's always multiple choice. And so that's good news because you can kind of piece it together and, process eliminations, narrow it down, and hopefully arrive at the right answer. There's also rarely more than one of them because it's just weird. So we're going to hit it. We'll only do the multiple choice on the homework. On the test, it's 2 multiple choice questions. So I want you to get it, but at the end of the day, if this one doesn't click, you're going to miss 1 question on the AP test. You'll be fine. So I don't say that about anything else because everything else sort of fits together. This is just, it's kind of tricky. With multiple choice, it's not too bad. So hang in there. Again, I'll sort of downgrade or eliminate some of the assignment to make it a little easier once we get there. All right, definite integrals and limits of Riemann sums. So we're still talking about the area from A to B. And we've done it with rectangles, right? For 4 rectangles, 6 rectangles. If you went crazy and did 8 or 10 rectangles, you'd be more accurate. But the purpose is to approximate the area under the curve. Like that's the name of the game here. And it's an approximation, right? Like we just got through talking about over and under, and so we know it's not perfect, but maybe it's close enough. We talked about this in some classes. How do we get a better approximation using Riemann sums? So how could we get a better approximation? What's that? Use more rectangles, right? So that would be like annoying if you actually had to calculate by hand. Instead of 4, you had to do 8 or 10 or 100. But if there was some way to, use a calculator or a computer or something to use more rectangles, then it makes sense if we stuck, 100 rectangles in there, then it'd be pretty accurate. So if we use n rectangles in a right Riemann sum, what is an expression for each little delta x? Okay, so we're going from A to B. And we want to know, I'm only going to draw one of them in there. So let's say we sandwich a whole bunch in there, and that little bitty distance right there is delta x. And there's n rectangles. So how would we figure out how wide that little delta x is in terms of A and B and n? What's the total width? How far is it from here to here? In terms of the letters I have, how far is it from here to here? In terms of the letters I have, A to B. So, okay, but if I say what's the distance from A to B? How far is it from 1 to 8? Answer it. You know it. 7. It's not a trick question. Okay. So from 1 to 8, we got 7. How far is it from 2 to 12? So how far is it from A to B? B minus A. The big one minus the little one. Now, if we want to divide that up into n intervals, it would be b minus a over n. So each little piece is the full width divided by however many widths there are, how many rectangles there are. Okay, let's find an expression for the height of each rectangle. Okay, well, let's put some rectangles in there. And we're going to use we end up using a right Riemann sum. Yeah, it says it right there. It makes the math easier if we use a right Riemann sum. So let's put some rectangles in there. Each width is delta x. Each width is delta x. And so the height of the leftmost rectangle, so that would be this rectangle. Leftmost rectangle has a height. If we're using a right Riemann sum, we would evaluate the function at, we wouldn't evaluate it at A, that would be a left sum. We're going to evaluate it at the right end. So what's the x value of what we're plugging into F in terms of letters on my paper? What's the x value of this spot right here? You're on the right track. Here's A. I want to go delta x beyond A. So starting at A, I want to go one more delta x over. There you go. A plus delta x would land me right there. And then F of that spot would give me the height of that rectangle. Okay, the next rectangle, that would be that x value and this height. So that height would be F of, so what's the x value right there? What's that, Tyler?
2 delta x.
2 delta x would just be that distance. A plus 2 delta x. And then the next rectangle, so one more over. I want this height. So that's F of, I started at A. I went 3 delta x's over. So evaluate the height. Find F at A plus 3 delta x. And so on. So in general, the height is, so let's follow the pattern here. F of A plus something. I need like I'm counting up here. And almost any time we need a counter in math, do you know what variable? Oh, there it is right there. Usually we use an I to be like our counter variable. When we're doing summations with the big capital S Greek sigma thing, a lot of times we use I equals 1 to 4 or 1 to 8 or whatever. I is usually our sort of counter. So A plus however many times we want to move over. I is the counter from 1 to n. All right, now the area of one rectangle is height times width. So we just said the height, F of A plus I delta x. And how wide is it? How wide is any one rectangle? Delta x. And I guess we could say right here, we could remind ourselves that delta x is b minus a over n. The total width divided by however many rectangles there are. Add up all, that sounds like sum from I equals 1 to n, because I is our counter. N is how many rectangles there are. F of A plus I delta x times delta x. So it's still the length or the height times the width. We're just adding them all up. That's what that summation thing out front means. add them all up. Now let the rectangles go to infinity. Okay, just keep adding more to this. Rectangles go to infinity. That sounds like n goes to infinity, right? The number of rectangles. So I'm going to write down that same equation, n equals 1, or excuse me, I equals 1 to n, f of I delta x times delta x. But this time, instead of just like saying, oh, let's go to 4 or 20 because we want to be accurate, like, no, let's let n go to infinity. So we're going to add this limit statement on there. Limit as n goes to infinity. So now this approximation isn't an approximation anymore, right? If we stick an infinite number of rectangles in there, we're going to have the area exactly. Okay, this is maybe the weird stuff. If we combine this together, let's see, we could use our stretched out s, because that means sum. And so what all of that equals, let's see, where's the best way to write this? This equals, I'll put it over here, the sum from a to b of f of x dx. Which is the actual area, not an approximation. Okay, I boxed this up, but this is not, like, you have to know this, but I'll show you how you have to know it and how we use it as we work some of these problems. Because the AP test likes to test to see if you can take one side and turn it into the other, or the other side and turn it into the other. You've got to be able to convert. Right, like from miles per hour to meters per second, but a lot more complicated than that. So I can give you the summation formula and ask you for the antiderivative look or the integral look, or I can give you the integral look and ask you to write the summation formula. Okay. Now, the good news is these are always going to be multiple choice. So you're always going to be kind of in the ballpark based on the options you have, and hopefully you can figure it out from there. Now, I said that our examples aren't multiple choice, but then once we figure out the examples, we'll do some off the homework together. Okay, so now we're on the one page that I just passed out today. Okay, so write that as the limit of a Riemann sum. So that means I know it's going to be limit as n goes to infinity of the sum from I equals 1 to n. Like, I know it's going to look like that. Let's add up all the rectangles. Okay, so now I need to remember my expression for the area of a rectangle is height times width. Let's see, width, but these are the individual rectangles. So the width of each individual rectangle, do you remember what that was? The width of each rectangle is delta x. And what is it for this problem? So what's the full width? 4. 7 minus 3 is 4. but then we divide by n because there's n number of rectangles. So my width is 4 over n. My width is b minus a over n, 4 over n. Now the height is f of something. Well, here's my function. So I know my height is going to be something squared plus 1. And this is where the multiple choice starts to come in if we had it. Like I would start looking at my answers and be like, I know it's got to look like this because it's got to be something squared plus 1. And chances are that would narrow it down to like 2 answers, and then you'd at least be guessing 50-50. So I've got to plug in something for x. Well, remember when we said we were going to plug in things, we started at a. We started at a, and we were adding, or we would move over each interval, and each interval was 4 over n. Each width was 4 over n. Yeah, delta x was 4 over n. So we start at 3, and we move over, I is our counter, 4 over n each time. Okay, so a couple of things. Those will match because that's our delta x. Maybe I should put this down here as well. A plus I delta x. Complicated. Let's try another one. Limit of a Riemann sum. So I know its limit as n goes to infinity, the sum from I equals 1 to n. So I'm adding up an infinite number of rectangles. And again, I don't have this formula memorized. I try to figure it out each time. So I know it's height times width because I'm adding up rectangles. And the width is b minus a all over n. Oh, what's weird about this one? It's sort of backwards. It's going to be negative, but that's okay. So it's still b minus a over n. The 2 and the 8 feel like they're in the wrong spot, but that's okay. Maybe I put that over here. Delta x is 2 minus 8 over n. So my width is negative 6 over n. And then my height is sine of, let's see, because I got to plug in the x value. I'm going to start at a and move over delta x each time. Starting at 8, put my counter on there. Delta x, we already said, was negative 6 over n. I didn't write this big enough to start with. Plus x, well, x is a, and then plus a plus I negative 6 over n. All right, why don't you try the third one? Limit of a Riemann sum. So we know how it starts. Maybe I should have left more room for height and width. So see if you can get number 3. Again, find the width first. I think that's the easiest part. And then it shows up. The width is part of the height because it's the function of where you're at. So find the width first and then start piecing things together. For A, B, and C, all right, it's all the same instructions. Find the limit as a Riemann sum. So limit n approaches infinity, sum from I equals 1 to n. Again, height times width. I know my width is 5 minus 3 over n. Total width divided by n, so that's 2 over n. So my width is 2 over n. And my heights are all natural log of something. Let's see, the something starts at 3 and goes up by a counter, I, times the width, 2 over n. Is this getting better? A little bit? Again, and with multiple choice, it's a little bit easier. All right, you write B. You tried it. So there's my answer for part B. Clean it up by getting rid of that 0. Don't have to clean it up. It was a safe stop. But now look at A and B. Look at the answers to A and B. What do you notice? They're the exact same. Let's think about that for a minute. What does 3 plus x do to a graph? What does x plus 3 do to the graph? You Algebra 2 transformation experts. Which way does that shift it? Left 3. That moves the original left 3.
Change the area, though.
Well, normally it would change the area, except that we also shifted our, look at our limits. We went from 3 and 5 to 0 and 2. So we also shifted those left 3. So we took our graph and moved it to the left. But we also took the interval we were looking at and moved it to the left the same amount. So whatever area was over here lined up, we move the graph, we move the interval, we get the same area. Kind of weird. Number 2 is the same thing, or part C is the same thing. I don't want to mess with part C. It's just one more example. But A and B are close enough that you can see, I think, conceptually what's going on. 3 plus x moves it to the left 3. And so if you also shift the window you're looking at to the left 3, then you're looking at the same shape. And so they're going to have the same area. It's kind of weird. Number 5. Ooh. Yes, but we're stopping at number 6. Or maybe we're stopping at number 5. We'll see. Which of the following definite integrals are equal to this thing? Okay, so we're going backwards here. Let's again start with the width. So I can look at this and I can tell already that b minus a needs to be 6. So b minus a needs to be 6. I'm good on 2. I'm good on 1. Okay, this is why we should have done C on part A. This 6 out front is gonna make up for that 6 right there. So I think that's gonna be okay. Let's see. This one starts at -5 and goes 6 away. So this means from like -5 to 1. So definitely this one looks good. -5 to 1 of tangent. 2 looks weird because there's -5 then is part of the problem, and you're going just from 0 to 6. So that one's good. This is weird. And then 3 is good because of that 6 out front. I'm not really worried about this one. They're all 3 right. And then let's skip number 6 because there's not one that bad on the test. Let's look at the worksheet, and maybe we can hit 1 or 2 on the worksheet, because this is what I really want you to be able to do, because this is what the problems look like on the AP test and on our test next Tuesday. So grab your worksheets. So we're only going to do 1 through 11. So if it makes you feel better, you could take the last page of that worksheet and tear it off and throw it away. All right, let's see if we can get number 1 and see how many we can get before the bell rings here. So if I'm going from 2 to 3, let's see what we can do here. My width is going to be 1 over n. Oh, well, I think I know my first one already, just based on the width. So what's number 1 going to be? It's got to be C, because that's the only one that has a width of 1 over n. By the way, the insides are all the same. 4x squared plus 2, 4 something squared plus 2. Let's see. This one starts at 2. I'm just kind of verifying. And then we go B away, delta x away. So yeah, number 1 is C. This is easy. They went first through 4. What's number 2 going to be? So the width is 5 over n. The only one that matches that is D. Number 3, the width is 3 over n. The only one that matches that is B. And then number 4, the width is the backwards one, but that's okay, negative 2 over n. That's got to be A. So for those, it was just matching up the widths to make it work. Now the next set, a little bit harder. Let's see if we can get number 5 done before the bell. So width is 6 minus 5 over n. So the width is 1 over n. So already I'm looking at E and H. So I'm looking at E and H. They both look like 3 times something plus 1. 3 times something plus 1, 3 times something plus 1. But which one of them starts at 5? Which one of them starts at 5? Which one of them has an A at 5? E or H? H, because there's my 5. That's my starting spot there. So 5 is H. 6 looks really similar. Width is 1 over n. But this one starts at 2. So that one's E. Okay, kind of tricky, but if we throw out the extra crazy, they're all crazy, but if we throw out the really crazy ones and we give you multiple choice, I think you can piece it together.